Hi, and welcome to this revision video on temperature changes, which is part of topic 8K energy transfers. So, within this revision video, we're going to focus on our knowledge of how we measure temperature and recapping that. We're also going to revise our understanding of the difference between thermal energy and temperature, and we're going to understand how we can determine the direction that energy will be transferred in. So some keywords for this topic are internal energy, thermal energy, heat energy, degrees Celsius, and evaporation. So a lot of us will be familiar through doing practicals that we measure temperature using a thermometer like the one on the right of your screen now. We would just read off the scale, so it looks like this one's about 20 degrees, and those units we use are degrees Celsius, which is that small little circle with a C. That's usually what we use in science for measuring temperature. And we should all be pretty comfortable with doing this from the amount of practicals that we've been doing throughout the year. So, temperature and heat energy are ever so slightly different, but they are linked. So, we can measure temperature, like we said, with a thermometer. But heat energy, which you'll also sometimes see referred to as internal energy or thermal energy, we can't measure. But it does depend on three important factors: the mass of the object we're talking about, the temperature of the object, and the material that that object is made from. So we think about this, the bigger something is, the more thermal energy it's able to store. So that's something that's going to change the amount of internal energy. The material it's made from, well, we're probably aware of how different materials heat up faster than other materials. So that's definitely going to have an impact. So for example, let's look at this question on the right. Which beaker contains water with the highest temperature? Well, we've got two beakers here, a large one at 30 degrees and a smaller one at 50 degrees. And remember we said temperature, we measure in degrees Celsius. So for this, 50 degrees is a bigger number than 30, so we can say that the beaker on the right is going to have water at the higher temperature. But part B says which beaker contains water that has the highest heat energy. Remember what we said, that it's not just now temperature that's important, it's also the mass involved. The beaker on the left is going to have water that is at a higher mass. Therefore, this beaker on the left is going to have a greater mass of water, which means it's going to contain water that has the highest heat energy. Not water at the highest temperature, but that water still in total has more heat energy, or more thermal energy, or more internal energy, whichever you want to call it. So have a quick look at these questions, and then we're going to go through them. There's just some examples of understanding which is going to have more internal energy, but also then trying to explain some scenarios based on this. So pause the video, and then we're going to go through it. So in the first one, we just have to decide which is going to have the most thermal energy. So a small mug of coffee at 80 degrees is going to have less internal energy than a large mug of coffee at 80 degrees. They're both the same temperature, one has a larger mass. A similar thing for the next one, a pot full of tea at 85 degrees and a pot full of tea at 95 degrees. Now they're the same mass, but one has the higher temperature, so it has the higher thermal energy. A swimming pool at 30 degrees versus a cup of tea at 80 degrees, we've now got two things that are different. However, even though the swimming pool is much colder than the cup of tea, the swimming pool has a much larger mass of water, and so is going to be able to store much, much more thermal energy than that cup of tea. Secondly, why don't you get burnt by the sparks from a sparkler? So this is a similar thing. Those sparks, they get incredibly high temperatures, but they're also incredibly light, very little mass. And therefore, because they have such low mass, each spark does not contain much energy. And that is really what, when you get burnt, it's that energy being transferred to you that causes you to get burnt. Why does it take longer to boil a kettle full of water than to boil enough to fill a mug? Similar concept, okay? You're going to need much more energy to boil a full kettle of water because there's much more mass there that needs to be heated to then bring it up to the temperature required for it to boil. So remember, these ideas of temperature and mass, temperature is linked with this idea of thermal energy, but with thermal energy, it's the mass that's also a factor as well as the material. So we can also discuss about how energy can be transferred from one object to another, okay? And just have a quick look. And from your intuition, what do you think is going to happen when these get mixed? So again, just pause the video, have a go at those questions, and then we're going to go over it now. So what happens is, energy is going to be transferred from the hotter object to the colder object. And if we mix these together, what's going to happen is we're going to meet somewhere in the middle. Because the hotter object is going to get colder, but that colder object is going to get hotter. And they're going to meet roughly in the middle. So that means, for example, with this first one here, when we have 10 and 20 degrees, if we just go roughly in between, we'll have 15 degrees. For 20 and 40 degrees, 30 degrees will be roughly in the middle. For 50 and 10, 30 degrees again will be in the middle. And here, because they are both at 60 degrees, it will be at 60 degrees. Notice, though, that we're ignoring the fact that some of this energy might be transferred to the surroundings. So we're just going to assume that it stays completely in those liquids. So the key thing from this is that energy is going to flow from the hotter object towards the cooler object. So that colder object is going to become hotter, and that hot object is going to become cooler until they are both at the same temperature. And to use a more accurate word at this stage, we would say equilibrium. But if you don't know that word at this stage, don't worry about it. So let's have a think about this, and let's apply it to a scenario here with a hot chocolate and a milkshake. So obviously the hot chocolate is hot, the milkshake is going to be cold. So let's assume that we've taken that and we've left it on a table in the classroom. What would happen to the temperature of the hot chocolate and the milkshake, the amount of heat energy in the two drinks, and the flow of heat energy then between the two drinks? So take some time, pause the video, and see if you can use what we have learned so far to then be able to pull your ideas together. So, firstly, we need to remember, okay, that really we need to identify, even though we know roughly what would happen, let's just identify what's going to happen here. A hot chocolate, if we leave it on the table, we know that's going to get colder, okay? You leave it on the table, it's going to get colder. The milkshake, if you left that on the table, it's going to get warmer. This is because the room temperature is colder than the temperature of the hot chocolate, but hotter than the temperature of the milkshake. So we can say that the temperature of the hot chocolate would decrease and the temperature of the milkshake would increase. Now, for the amount of heat energy in the two drinks, well, they're different materials, they might be different masses, but apart from that, the only thing that's changing for each of them is their temperature. Remember, if we have more temperature, we're going to have more heat energy. So if the hot chocolate is losing temperature, its heat energy is going to decrease as well. The milkshake, if its temperature is increasing, that's the heat energy of the milkshake is also going to increase. And if we look at the flow of heat energy between the two drinks, if the hot chocolate is losing heat energy, but the milkshake is gaining heat energy, we can say that the heat energy would flow from the hot chocolate to the milkshake. It's going from the hotter object, the hot chocolate, to the colder object, which is the milkshake. So that is how energy is going to flow. So to recap, we have looked at how we can measure temperature using a thermometer and how we use the units of degrees Celsius. We have also looked at the difference between thermal energy and temperature, and how thermal energy is going to depend on temperature, the mass of the object, and the material that the object is made of. And we've looked at some examples where we've got different sized objects at different temperatures and been able to determine which is going to have the higher thermal energy. And remember, we can also use the words internal energy and heat energy here. And finally, we've also looked at how we can determine the direction of energy transfer, being from the hotter object to the colder object, until both of them reach the same temperature.